All right, this is Mr. McMurray again. We're still here on Chapter 3, and we just started talking about how kilograms and newtons are the equivalent of each other. And let me just go over a little bit more of that real quick. So first of all, kilograms have to do with mass, and mass, we said, does not change. It's how much matter there is in something. That is going to be measured in grams of some sort. Or if you have 1,000 of those, that would be a kilogram. A dime is about 1 gram, so a gram is a fairly small amount, and that's why a lot of times we use kilograms, because that's a lot more practical amount that something's going to have. If we're very heavy, we're going to have a fair amount of kilograms in it. Okay, and if we were going to weigh a kilogram on a scales, we're measuring how much gravity is pulling down on that kilogram, and our answer would be in newtons. And if we did that, officially, 1 kilogram would weigh 9.8 newtons. And we're going to round that off and say 10 newtons. So up here you see if you have 1 kilogram, it would weigh 10 newtons. And for the most part, it would weigh that anywhere on Earth. If you could get high enough or in a pit low enough toward the center of the Earth, you might be able to change it just a smidgen. But for the most part, anywhere on Earth, the force of gravity is going to pull down on 1 kilogram so that it weighs or exerts a force of 10 newtons on it. Okay? Now, if that kilogram, if we're going to say how much it weighs in pounds, which is what we're used to thinking of weight in terms of, it would be 2.2 pounds. Okay? About 2.2, a little over 2 pounds for a kilogram. So newtons would be the metric way of measuring how much something weighs, and pounds would be the English system or the older system, standard system, a way of measuring how much something weighs. But since they're both types of weight, then we can convert from one to the other, and 1 pound is equal to 4.45, or we'd say 4.5 newtons. So if someone asks you how much you weigh, for example, I weigh about 200, I can say, well, I weigh 900. They say, whoa, what a heavyweight. But that's true, it's 900 newtons, but only about 200 pounds. And it would probably mean that I have a mass of a little bit less than 100 kilograms. Right? Just to kind of put things in perspective there. Roughly speaking, if you took the number of kilograms and multiplied by 2, that would roughly give you how many pounds it would be the equivalent of. All right? So keep in mind, pounds and newtons depend upon gravity, okay? And they are a weight. And the weight is based on the kilograms, how many kilograms gravity is acting on. If we were someplace where there was less gravity, then everything would weigh less pounds, but there'd still be just as much of you. If you went to the moon, you don't lose any matter or any of your body. It's all still there, but it would just less gravity pulling down. It would make you less weight. So instead of being weight challenged, we should just say that we're gravity challenged. All right, and if we had less gravity, that wouldn't be a problem. That's how I like. All right, so go back to Newton's second law. We were talking about there's a force that we need to talk about that's involved in that, and that is the force of friction. Okay, and we're all fairly familiar with friction. Okay, friction is a force, but you don't always see it. For example, if you roll a ball on the floor, Newton's first law says eventually it will stop if there are forces acting on it. Otherwise, it'll keep going at the same speed. And so the reason the ball slows down is not because it runs out of force, but because there's another force besides your pushing force that slows it down, and that would be the friction of the ball touching the floor. Okay, and so friction is a force that we'd like to talk about here just a little bit. All right, if we think, oh, we kind of know all that, but we need to kind of look at it again in a little more detail. Say you have a crate, okay, it says peaches, whatever, big old crate full of peaches, all right, and it's sitting on the floor. If it's sitting there, there are two forces acting on it. One is weight, gravity, pulling it down against the floor, and there's also a force pushing up on it. That's the normal force, or the support force we talk about, okay? If it's just sitting there, is it accelerating? No. Okay, so there's no acceleration. And that means the net force on the crate must be 0, because if there's more than 0, there would be an acceleration or deceleration, either positive or negative acceleration. It would be changing its velocity. But since it's just sitting there, we know that the net force is 0, and that means that there is no acceleration. All right. Now, if we took the same crate, let's change conditions a little bit, and say now we start to pull on a rope that's attached to it. All right. Now we're starting to pull on a toy. It's not enough to make the crate stop moving. Now I'm starting to pull on this crate, but so this is getting stronger. I'm pulling with more force this direction. However, if the crate is not moving, I know that there must be a net force of 0. And if I'm pulling here, then that means there's some force that's canceling out. But it turns out that is the force of friction, or F of F, down here at the bottom. The friction between the crate and the floor is equal to the pull that I'm putting on here, the force that I'm pulling with. Now say I pull harder, but the crate is still not moving. This has increased. P has increased. What has happened to the force of friction? Since the net force is 0, it must also have increased. And it will continue to increase as I pull harder and the box does not move. Okay? So right now we know the force of friction which acts on is equal to P because it's staying still, it's not beginning to move. They're canceling out, causing the net force to be 0. Okay? And so that was what will happen. As I begin to pull on the crate, the force of friction will increase. Now, it can only do that to a certain point because based on how rough the floor is and so forth, okay, then it can only have so much friction, and then it will begin to move. Alright? Now, if it begins to move, alright, let me get all these right here, okay. Alright, now it is changing its velocity, correct? It's beginning to move this direction from going 0, velocity of 0, now it's beginning to move. So that tells me the net force must be greater than 0, otherwise how could it be moving? So it's greater than 0. And since the net force is acting to the right, because P is bigger than F of F now, the acceleration is going to go toward the right. So it's going to accelerate, okay? Now, at some point, this is a big heavy crate, I can't just keep going faster and faster and faster, which is what accelerating is. And so at some point I am going to probably slow down to where I am pulling it now at a fairly steady speed, okay? And so now we're going at a constant velocity, okay? If we're going at a constant velocity, that means we're not accelerating. And so the friction force has to be equal to P. Okay, they are equal to each other, which means I'm not speeding up or I'm not slowing down, I'm not accelerating. So the net force is 0. Notice the crate is still moving at a constant velocity. Okay, just because the net force is 0 does not mean it will not keep moving. It means it will keep moving at exactly the same velocity. Okay, so it has a constant velocity. That means the acceleration is 0. It's not speeding up, it's not slowing down, it's not changing direction. And the net force on the crate then has to be equal to 0, since there is no acceleration. All right. Now, some of that seems a little confusing sometimes, but just keep in mind that net force of 0 means there's no acceleration, which means the object either stopped, which means it's not changing its velocity, or it's moving at a constant velocity and it's not going to speed up or slow down, so it's going at a constant velocity. Okay. A net force of 0 does not necessarily mean that it is still, although a still object would have a net force of 0. It can be moving, it would just be moving at a constant velocity. Alright? Alright, so that kind of has to do with friction. So I want to talk about that a little bit. We'll be doing a lab, hopefully, on that also. Alright, now, Galileo did a lot of experiments, and among his experiments, he found that the objects accelerated at the same rate. He could take big objects and small objects, and they would accelerate down his ramps at the same speed. Okay? And this is something he disproved from Aristotle. Aristotle said that if you have a heavy object, then it's going to fall faster because it weighs more. Therefore, it's going to fall faster. Whereas Galileo actually demonstrated that if you took he took 2 cannonballs stuck together, so they weighed twice as much, and a single cannonball, dropped them off, theoretically, the Tower of Pisa, and he dropped them and they hit at the same time. And so he proved that no, they do not hit at exactly the same time. Okay, but he couldn't really explain why. He would take different size balls on his ramps. Okay, we kind of talked about his ramps earlier. These are some different ramps, but He took balls on his ramps and he put big balls on them, and they accelerated at the same rate as the small balls did. So he proved that that was true, but he couldn't really explain why that was true. Okay, and Newton's law, as part of what Newton did, he didn't completely come up with a new idea, but he explained how you could have two objects of different mass and they can fall at the same speed. Alright, so let's look at this example here. Alright, we have a big rock and a small rock. Okay, we know that the mass of the big rock is going to be big compared to the mass of the small rock. Okay, now what force is acting on them to make them fall down? Well, gravity. And gravity depends on the mass of the object. If there's more mass for it to act on, then it will weigh more, and it will exert a greater weight or force pulling it down. A smaller rock that has less mass will also have a less force of gravity pushing on it, so it has less weight, and therefore it will not have as much force pushing on it. So, for example, say this rock weighed, had a mass of, let's just say, 4 kilograms, and this one over here only had a mass of 2 kilograms. Okay, but the force of this, or the weight, would be 4 also, and the weight of this one, let's just say, would be 2 also. So even though this one has more mass, which we'd expect to make it fall, so it also has more weight, which would make it fall faster, and that cancels each other out. This one has a small mass, so I think, well, it's not going to fall very fast, but it also has a small amount of force pushing on it. So if you divide a 4 by 4, you get 1. If you divide 2 by 2, you get 1, and they would both fall at the same rate. Now, that's not exactly correct. Actually, the force would be 40, because it would be about kilograms times 10, and this one here would be 2 kilograms times 10 would give you 20 newtons. All right, and so you would actually get up that this one would fall at 10 meters per second, and 20 divided by 2 would also give you that this one would fall at 10 meters per second. And so they would fall at exactly the same rate. Okay, they would accelerate at the same rate because their accelerations would both be 10 meters per second. They would be speeding up at 10 meters per second squared. We'll talk more about the units later, but that's the point. So Newton's law explained why if something has a large weight, it also has a large mass, which means it has a large inertia, and it doesn't want to start speeding up or change its speed very much, so that it resists the force, and therefore they kind of cancel each other out, and all objects will fall at the same speed. Now, someone says, well, but say I drop a feather and a rock. They do not fall at the same speed, and should be the same thing just because the feather is lighter, it should still fall at the same rate as the rock or coin or whatever else, because all objects, we said, fall at the same rate. So the question is, how does this work? Well, the phenomenon that interferes in this is friction again. Okay, let's go back to Newton, Galileo's ramp. He found that as he got the ramp steeper and steeper, they would fall faster and faster until finally, if his ramp were straight up and down, they would just fall straight down. Okay, now, this speed would work, but so he said big objects, small objects would fall at the same rate. Heavy objects and lighter objects would fall at the same rate. Why then does a coin and the feather does not? Well, part of the problem is there's another force involved. If it were just gravity, then that would in fact work. In fact, we'll look at the video, if we watch the video here a little bit, of the on the moon where there is no atmosphere. You will notice gravity is the only force, and though they fall slower than they do on Earth, both a hammer and a feather would fall at the same rate. However, on the Earth's surface, there is another force acting, just like the ball we talked about earlier that was rolling across the floor. There is a force, and that force is friction. All right, so we're going to stop right now. We're going to come back in just a second in the part 3 and talk about how friction affects objects that are falling through the air.